we have given a list of relationships between a point and a set in a topological space, and we have seen that it is the notion of a limit point of a set which formalizes, which precisely describes what it means for a point to be arbitrarily close to a set. And in fact, the first result concerning that was that a set in a topological space was closed if and only if it contained all its limit points. That is, closeness that's equivalent to including all points which are arbitrarily close to itself on the part of a set. We also give simple characterizations for openness in terms of every point being an interior point, or in terms of the set being a neighborhood of each of its points. Now, of course, there are two things which remain to be dealt with in this section. One is, well, what about A interior, A closure, and boundary of A? Will they always be open or closed, irrespective of what set we consider? That's one. And the second is, going back to our pictorial questionnaire, well, closeness was identified with containing the entire boundary. Openness was identified with excluding the boundary entirely. Whether that's true in general or not, we'll continue with that. So we can start with a proposition directly. That X tau be a topological space and A a subset. Now, firstly, A interior will always be open. The closure of A and the boundary of A will always be closed. Secondly, A is open if and only if A is equal to its interior. Well, in fact, we have already proven this, because an interior point, by definition, is a point of the set. Thus, A interior is contained in cap A. On the other hand, A actually is open if and only if every point of cap A is an interior point, which simply means that A is contained in A interior as well. But that if and only if A intersection its boundary is empty. Now, this tells us the pictorial yardstick we used, that's true in general. The picture is not misleading. We can trust the picture in this case. Thirdly, A is closed if and only if A is equal to A closure. Well, again, we have proven this, because any point of A, well, is either an isolated point or a cluster point of A. Thus, it's in A closure. That is, it's a limit point. Conversely, now when you consider A closure, well, That's the set of all limit points. Now we have shown that A is closed if and only if contains all its limit points, which in terms of these notions is equivalent to saying that A closure should be contained in A. A closure is the totality of limit points. If every limit point should be in cap A, that means A closure should be in A. We have proven this as well. Now, that's equivalent to the pictorial yardstick we used. That is, A should contain its boundary entirely, its entire boundary. Now, it is useful. It is a useful exercise. It's instructive to go through the proofs of the statements which have not been proven so far, because that is just you deal with the definitions. You use the definitions and you get the result. But now this also tells us the following. Now A interior is open. No matter what set A you consider, A interior is an open set contained in A, in the set. But is that the largest open set contained in cap A? Can we find, suppose A is not open, then A interior is contained in cap A, but it's also a proper subset of cap A. The question is whether there could be any open set, any intermediate open set containing A interior and contained in cap A. Well, you can easily see that's not the case. So A interior is the largest open set contained in A. Well, A closure, on the other hand, A closure is closed. No matter what set A you take, A closure is a closed set containing A. Well, this time we approach A from above. The question now is whether there can be, if the set is not closed, A is a proper subset of A closure. Could there be any intermediate set containing A contained in A closure, but not equal to A or to A closure, which is closed? Well, you can again see that that's not the case. I will leave the proofs of the two statements as an exercise to you. A closure turns out to be the smallest closed set which contains A. Now, we can actually, and here, smallest and largest with respect to inclusion between sets. Well, B contains A, that's what we consider B being larger than A. But now we can express this in the following form. Now again, let X tau be a topological space and A a subset of the space. Now one. A interior, this in fact will turn out to be equal to the union of all open sets which are contained in A. That is, it's the union of the following collection, G, a subset of cap X of the space, such that G is contained in A and G is open. Now this automatically will imply that actually the interior of A is the largest open set contained in A. Why? Take any open set contained in A, that will be a member of this collection. Well, then it will be a subset of the union over the entire collection. Likewise, a closure that can be characterized as the intersection of all closed sets which contain A. This time C contains A and C is closed. Of course, by the open and closed set properties, this will be open and this intersection will be closed. I will leave the proof of this also as an exercise too. Now, that takes us to a new section. Now, eventually, we will be interested in Euclidean spaces in economic theory. Mainly, well, there will be, of course, exceptions to that, and it's useful to know what the more general framework is. But Euclidean spaces are metric spaces, and metric as a generalized distance is actually a less abstract, relatively more concrete notion. Now, it would be nice if we can make life simpler in metric spaces, utilizing that this notion of a generalized distance is something easier to conceive, easier to deal with. But if you wish to make life simpler, well, then you need tools which will accomplish that aim. And now, an important tool which is used in characterizing topological properties of metric spaces is something which is familiar to you, well, from high school on. It is the notion of a sequence. So we'll have 1 point something. It will be about sequences. Well, as we have been doing in each case, let us again start by giving a formal definition, a precise definition of what a sequence is. Well, if, for example, you have a sequence in real numbers, well, you can write that x1, x2, xn, and you continue like that. It's an object like this, where x1, x2, xn are real numbers. But how can we formalize this without using the everyday meaning, without basing us, relying on the everyday meaning of a sequence? Well, here the position is important. Here x1, this real number, is associated with 1. Here x2, this real number, is associated with 2, and so on. So a sequence is nothing but a function whose domain is the set of all natural numbers. And if it's a sequence of real numbers, the range is the real numbers. But we don't need to confine ourselves to real numbers as the range. Well, you can take, for example, the set of 7 colors and then having a sequence, say yellow, red, red, blue, green, yellow, and so on. That would be a sequence. That again can be represented as a function defined on the set of natural numbers, but this time with values in the 7-element set, well, the 7 colors, the 7 fundamental colors. So we can take this and define a sequence in a set. Well, let A be a non-empty set. A function, say, let me use x to denote the function, no problem, I can use anything, on A with values in A is called a sequence in A. But when we denote a sequence, we usually do not use this functional notation. Given a sequence X, for each n in n, we write now here, using the functional notation, each n is sent to the member of cap A, which is denoted by x sub n. Well, we prefer the shorter notation x sub n instead of this. More, while also, we also write x sub n for the function x. Okay? So that's the usual notation. But when a sequence is given, be it in high school, in your undergraduate studies, or at whatever level, you're interested in, well, is this sequence convergent or divergent? These are the two major notions that we associate with sequences. But for divergence or for convergence, well, in calculus, when we deal with real numbers, we use the usual metric, the usual distance. But here, we can do that in general metric spaces. So but we need a metric structure. Well, we do not know whether just a more general topological structure will be useful or not. We'll see that in a minute. But let's first define convergence and divergence in a metric space in general. So, now let Xn be a metric space. Xn, a sequence in cap X, and A, a member of cap X. Now we'll define what it means for the sequence Xn to converge to A with respect to the metric M. We say that Xn converges to A. And, well, let me also introduce the notation we use for that and write Xn with an arrow if. Now, let me define it in a way which also will make perfect sense in a general topological space. Well, what does this? Well, the members of Xn, as you go out in the tail of the sequence, as n gets larger, they get closer and closer, arbitrarily close to A. That's what we mean when Xn converges to A. But now, well, we have the epsilon ball notion in magic spaces. In general, that was replaced by the notion of a neighborhood. So, well, we can then express that given any neighborhood U of A, the members of the sequence from some point on will belong to that neighborhood. So let's take that as our definition. If for every neighborhood U of A, well, the domain now is the set of natural numbers that is some such that whenever n is larger than or equal to k, so that actually refers to the tail of the sequence from the cap k term on, Xn belongs to. Okay, so this is just a very reasonable definition for Xn to converge A. Now, when Xn converges to A, well, let me to A with respect to M. At least in the definition, let me write that, but we will suppress it if the metric used is well understood as always. When Xn converges to A with respect to M, we refer to A as a limit of Xn. Well, we do not know the uniqueness. If it's unique, well, both problems. Well, given a sequence and given a point A, well, Xn may not converge to A, but if it converges to A, there might be other points to which Xn converges as well. So that's why we're careful and we refer to that as a limit. Now, moreover, we say that Xn is convergent. Everything with respect to M, but I will not write that anymore. If Xn converges to A for some X, otherwise we say that is if there is no such A in cap X, we say that Xn is divergent. All with respect to M. Now, before proceeding any further, let us see how the general situation, how the conceptual location of sequences in general topological spaces. If I had written here X-star topological space, and instead of with respect to M, with respect to tau, what I have written so far, everything will make full sense. But now let's consider the following example. Let X be a topological space. Well, let me first take a non-empty set. Let me start with that. Be a non-empty set. And tau. Now we have the two extreme topologies. Now let's first consider the coarsest one, the indiscrete topology. Let Xn be any sequence in X and A any point in cap X. The question is, well, will this arbitrary sequence Xn converge to this arbitrary member A of cap X? Well, let's check. Let us take any neighborhood that U be any neighborhood of A. But what do we know about U in that case? It has to be the entire space, cap X. That's the only open set which contains X. Then U is equal to X. But now let's check whether this condition is satisfied. But this is a sequence in cap X, means that Xn, no matter what n you take, is a member of cap X, is a member of U. Well, so for all n in n, we have that Xn is in X, which is U. But what does that mean? Well, that means Xn converges to A with respect to tau. So Xn converges to A with respect to tau. So it's not telling, it does not distinguish between sequences and between points which are limits of sequences. Every sequence converges, and every sequence converges to everything. Well, that does not give much information. Sequences will not be an appropriate tool to distinguish between different topological phenomena in this case. But let's consider the other extreme. The other extreme is when we take, now let me write this tau 1, set tau 2 the discrete topology, that is 2 to the power x. We know that this is metrizable, so we're back to the world of metric spaces. Let Xn be a sequence in X and A in X. When will Xn converge to A? Let's check. Well, here, the smallest possible neighborhoods of A will give us more information. But what is the smallest neighborhood of A? It's singleton A itself. Singleton A is open. Now, is a neighborhood of lowercase a. But that means if this sequence converges to A, it must be a constant sequence from some point on. Any finite initial segment, that's irrelevant. Now, so Xn will converge to A if and only if there is some natural number k such that for all n larger than or equal to k, Xn will belong to singleton A. That is, Xn will be equal to A. So here we have the other extreme. In the case of the indiscrete topology, everything converged to everything. Here, convergence is restricted to essentially constant sequences. The sequence has to be constant from some point on. But if you look at the definition of convergence, well, any initial segment which is finite, that's irrelevant, because we're interested what happens out in the tail. Okay. Now, this was actually a pathological behavior exhibited by a topological space which is not metrizable. But here, well, Xn, if it's convergent, you can easily see, well, it will be constant from some point on. Therefore, it will have a unique limit. But that will be in general true for all metric spaces. But let us now make this more specific instead of U. Let's start to make life simpler for us. Firstly, a simple proposition. We can replace neighborhoods over there by epsilon balls, and that will be equivalent to the original definition. That is, let Xm be a metric space. Xn, a sequence in cap X, and A in X. Now, Xn converges to A if and only if. Now, well, instead of for every neighborhood, well, we'll replace that by for every epsilon ball about A, but that means for every epsilon positive. There is some k in n such that from that point on, for all n larger than or equal to k, well, here, of course, n should be a natural number as well, but that will be well understood, so I will not make the notation heavier for that. X sub n is in the epsilon ball about A with respect to the metric M. Well, that is simply M A X n is less than epsilon. This is another way of writing this. Well, the proof of this is almost obvious. Well, given an epsilon ball, that will be a neighborhood. Thus, if this converges, assume that this is convergent. Given any epsilon, the epsilon ball about A, that's a neighborhood. So there should exist some such K with this property by definition. Okay? Now, conversely, assume that the right-hand side holds. Now we are to prove this, but the original definition is given in terms of neighborhoods. Well, then take any neighborhood U of A. but that will contain an epsilon ball about A entirely. This tells from some point on, all the terms of the sequence will be in that epsilon ball, but that epsilon ball is a subset of the original neighborhood you started with, so the result follows. Okay. Next, uniqueness. Now we'll take this. Well, let me take this part, leave out this. Now, xn can have at most one limit. That is, the number of limits is either 0 or 1. Well, if divergent, it has no limit. If convergent, this says uniqueness. But let's go through the proof of this. Suppose there are A, B in X with A different than B, such that xn converges to A and xn converges to B. If this leads to a contradiction, the job will have been accomplished. But here we use the same trick. A and B are different points. We're in a metric space. So M of AB is positive. I can take M of AB, take half of it, set it to equal to epsilon. Then I can have two epsilon balls, one about A, one about B, which are disjoint. Well, this will mean after some point, all the terms in the sequence belong to here. And this says, well, after some point, everything is in here. But that cannot be the case. But let's write that in a precise form as well. Now, since A is different than B, M of AB is positive. Set epsilon equal to 1/2 of that. Now, since by supposition the sequence xn converges to A, given this epsilon, there is some, say, k1 in n, such that for all n larger than or equal to k1, we have that xn is in the epsilon ball about A with respect to m. But since xn also converges to B, there is some k2 in n such that for all n larger than or equal to k2, xn is in the epsilon ball about B. Okay? This should actually yield us the desired contradiction. But now, if I take the larger of the two numbers, k1 and k2, if I set that equal to cap k, everything beyond that, including the cap k term, they should belong to both of these. So set k k equal to the maximum of k1, k2. Now, x sub k that belongs to b m epsilon a and b m epsilon b. Huh? So from the picture, that should lead to a contradiction. But let's see that it really does. Now, what's m of AB? That's 2 epsilon. Because we defined epsilon as 1/2 of m of AB. But now it says there is something xk belonging to both. So, well, I can take the triangle inequality involving this triplet. This will be less than or equal to m of a xk plus m of xk b. What do we know about this? Is less than epsilon because x sub cap k is in the epsilon ball about a. This is less than epsilon. What about this? Well, this is less than epsilon as well because x cap k is also in the epsilon ball about b. Less than epsilon, so this is less than 2 epsilon. Now what we have obtained is 2 epsilon less than, strictly less than itself, a contradiction. So that completes the proof. Thus, if a sequence is convergent, then it has a unique limit when xn converges to A with respect to m in xm, we write A is equal to limit xn. Because this will be unique, like in supremum of a set, infimum of a set, maximum, minimum, and so on, we can write this. Okay. But what's the use? How will this notion, sequence, how will that make actually life simpler? Now, in economic theory, in equilibrium theory, existence of equilibria, or whatever, when you're interested in having some equilibrium, the existence of some equilibrium, you will have to show that certain sets are closed. And if you go through all the papers and textbooks, if that set is in a Euclidean space or in a metric space in general, the way you do is the following. You take any sequence in that set which is convergent and show that its limit belongs to the set. That's equivalent to closedness of a set in a metric space. Now, well, we'll show that, but that will come as a corollary of the following result. And that also will be telling about the naming we use. But let me just write the result, which will prove proposition let xm be a metric space A, a subset of X, and X in X. Now, X is a limit point of A if and only if X is the limit of some convergence sequence in cap A. X is the limit of some convergent sequence Xn in cap A. In cap A, all the members of this sequence should belong to cap A. But once we have this, we know that a set is closed if and only if it contains all its limit points. Well, then it follows a set is closed if and only if it contains the limits of all convergent sequences, all of whose members belong to the set. And this is actually where this naming limit point comes from. A limit point is the limit of some convergent sequence in the set. Now let's prove it. Okay, let's delay the proof to next hour.